Hello, this is a tutorial on the new flow-down surface force component in the latest version of Quelea for Grasshopper. I'll just show you, it's more interesting. This force is really meant to simulate how, maybe rain particles flow down the topology of a surface. So here you could see, a simulation if rain particles landed, on these points on the surface. Some of them aren't being displayed properly, but if they were land here, how would they travel and where would they end up on that surface? So you can see it behaves as expected. And this idea and the kind of the computations behind it were taken from Wu-Jae Sung. This is his blog. And he has this nice PDF going over exactly how this, how this thing is computed. And this guy, Hyder Alward, was also useful. He implemented a version of it using Grasshopper components and HoopSnake. But it looks, it's a lot more complicated to put together. This was his script. And this is the one for Quelea, where you just have your basic setup and then your surface flow. And there are a few particulars that I'd like to go over. So in order to set up this scene, what I have is I have my surface, and then I divide it, and I get these points by subdividing it. I feed those into my emitter, so now I have multiple emitters, right? 121 emitters. And each emitter is able to generate one agent and then stop. So it just generates one agent at the beginning and then stops. That's why continuous flow is set to false. So it doesn't emit one every time step. The other thing I have set up here is that the initial velocity is set to 0. So rather the initial bounds of the initial velocity is going to be set to 0. This is so that the particle doesn't get initialized with some random velocity in some direction that's going to affect the how the rainwater would fall. So this generally just wants to be 0. Of course, I have their license head set to 0, and then I also have a large history link so I could save their trail. The other thing that I do here is I actually use the polysurface environment instead of a surface environment, because right now the surface environments don't work well with 3D forces. It's something I'm going to fix in the future, but for now you can just use a polysurface environment. It's going to work just as well. So that's the polysurface environment, and then coming out of the deconstruct system component, you actually are just going to need this one flow down surface force. And the thing that I do, I also added this set velocity component as well. So this allows you to actually just kind of hard set the velocity. So this is a behavior because it's going to alter the state of that particle. And it's going to set that velocity. I'll explain why I do that in a second. And then I just have some preview stuff going on here. So that's that first surface. I'll just run this again, and then I'll show you it. Here's where it gets kind of weird. So for this component, I've actually am saying don't apply this force. So if I were to disable this component and then run the simulation, you see nothing is going to happen, because while the force is being calculated, it's not being applied to the agent. Now if I were to set this to true, you would see that force is applied, and you would also see that it doesn't really behave as expected. So in this case, because it's a force, the momentum of the particle is a factor. So it's almost as if this was, maybe raining on top of a sheet of ice or something. So where the particle's momentum, forward momentum, is going to affect even how that surface is sloping isn't going to directly control the velocity of the particle. So that is why I use this set velocity. So actually I won't apply this force at the time, and rather I'll just set its velocity to be this vector at each time step, rather than a force that's applied and based on the particle's mass and the particle's current velocity. By just setting the velocity, it allows it to have this effect, the kind of more realistic or maybe more informative effect of how the particles behave regardless of their current velocity, not taking momentum into account. All right, maybe that was too long, but I actually want to do another one. So with this component, it's also going to work for polysurface environments, which is pretty cool. It's just something even Ujie Sung's script and the other guy's script aren't going to currently work with polysurfaces. So to show you that, I am going to switch over. So this is my B-rep. So I'm going to use, instead of this surface as my polysurface environment, I'm going to use this B-rep. All right, so now this is my polysurface environment. And the other thing is I compute some points along the surface using surface subdivision in this area component. And these are going to be my starting positions. And I'm just going to hide these and hide this as well. So now we have our starting positions on this surface, and let's just run and see what happens if we don't change anything. Not great, but not wrong either, because the surface does kind of slope in the middle. Particles, it is being affected by the slope of that surface. But I found that for this surface in particular, and maybe polysurfaces in general, it is actually better to use that surface force. So here I'm just previewing it. I'm using the surface force, but the other thing, so for one, we're going to control this step distance. This is kind of the distance that it's going to send a test point out to see the velocity or the slope of that surface at the next point. So this was a very large number. It's going to kind of do a test point that's farther away from its current position. So if you want a very accurate simulation, you're going to want to set this very low. So this is set at 0.01. So let's try that. Let's just try if we do that. So we get a little better result by testing points that are only very close. Before it was set to, I think the default is 1, 0.1. This is 1/10 of that, and you get a little better result. And you can see they're also kind of moving pretty fast. This would be a very slick sheet of ice. So the other thing I do is I kind of use this weight almost as kind of a friction component. So the friction component of a force would act, in the negative direction of the velocity. We can simulate this by just multiplying that velocity by some number less than 1. So here it's 0.1, so take 1/10 of that force and apply it, and you get a much better result of that simulation. I think that this might even look better without those trails. And now you could see how those rain droplets might travel along that surface, and where they're going to get stuck, and where they're going to actually be able to run off the side of it. All right. Let's show you that one more time. All right, so for this project, this was a project I had done back in 4th year, I think, of my architecture school, and the concept was that this roof would drain the rainwater. This was next to a river in Pittsburgh, and so it was in a floodplain, and so the whole concept was that it would drain the water into the river. And so now we could see through and I wasn't able to test this at the time, so I just came up with a surface that I thought might do that. You can see that there. But I wasn't able to test it. So now with this new component and Quelea, I would have been able to kind of see that they're not all being drained to this point, which is what I was going for. They could get stuck over here. There's some low point that exists there. And then even at the top of the surface over there, we can see that there's also a low point where they're going to gather and not be able to run off and kind of get stuck. So I might go in and alter this surface after the fact, after I've done this analysis. There you go. I hope that was useful. You're going to have to play around with this component and find values that work for you. This is certainly not a scientific simulation of rainwater, but it will definitely be able to give you a good sense of how the water might flow over your surface. It would certainly teaches me that the surface I came up with was not optimal to drain all the water to one point. So I might go in and change that. So there you go. Good luck, and I'll see you in the next video.